All right, for homework number 12, the first problem wants us to verify that this infinite series converges. So they're listing out a few of the terms, but we don't really need the terms listed out. If we're doing convergence, uh, this is a geometric series. So r is equal to negative 0.6 or well, no, I'm just going to leave it like that. You could change it to a fraction that's negative 6/10 or negative 3/5. It doesn't say find what it converges to, so I'm just going to verify. So since the absolute value of r is between 1 and 0, this series converges by the geometric series test. If it said what does it converge to, I would use r as negative 0.6, and I would find a sub 0, which is 1, and I would do the math on that. Find the sum of the convergent series. So here is where these are geometric, and I'm going to do that for these first two. So r is 1/2, which is less than 1, so this does converge. This series starts at 0, so find the first term, which would be a sub 0. That's 1/2 to the 0, which is 1. So this convergent series will equal 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. So this converges by the geometric series test. For the next one, r is equal to negative 6/7. That's between 0 and negative 1, or whatever. It's a fraction that's small enough to decrease or approach 0. And then a sub 0, because that's where this starts, would be 3 times negative 6/7 to the 0, so 3 times 1. So this one will be 3 over 1 minus negative 6/7. So that's 3 over 7/7 plus 6/7 is 13/7. And then when you multiply this 3 times 7/13, you're going to get 21 over 13. Now, the next series is not geometric. It's not a times r to the n. This is possibly one of those telescoping series. So the first thing we want to do is separate this out using partial fraction decomposition. So just like I did with integrals, I want to leave a little bit of space here. And one of these will be 1 over n. And then the other series will be 1 over n plus 2. And we're going to use that cover-up method that we did in Chapter 8. So remember, you're saying, if n equals 0, I cover up n, and I plug 0 into 4 over n plus 2. So I would get 4 over 2. And then if n equals negative 2, I cover up the n plus 2, and I plug into 4 over n. So that's going to be negative 2. All right, so we've rewritten the problem. So now it's a difference of 2 series. And remember, if this were truly telescoping, then we could just say, it'll be the first term minus the limit of the last term, call it a day. But these two denominators are not a difference. Like if this is b sub n, this is not b sub n plus 1. That would be 1 over n plus 1. So I just point that out to say, and you could do this with whether it's truly telescoping or not. All this is saying is we need to go ahead and expand out what the terms would be and just see what would survive and what would cancel out. So I'm going to condense this a bit. They both have a 2 in front. They're both starting at 1 and going to infinity. And then we have 1 over n minus 1 over n plus 2. All right, so we're allowed to condense this into one summation. That's one of our sum properties that we learned on the first day of these notes. And so let's just expand this out. So there's a 2 out here. And then when I plug in 1, what would I get? I would get 1 over 1 minus 1 over 1 plus 2, so minus 1/3. When I plug in 2, I would get 1 over 2 minus 1 over 4. When I plug in 3, I would get 1 over 3 minus 1 over 5. Plug in as many numbers as you need to plug in to help yourself figure out what's going to stay and what's going to cancel. So I'm going to do one more. Well, I'm going to write out 2 more things. So I ran out of room over here. So if I plug in 4, I get 1/4 minus 1/6 plus ... So let's look at what's canceling so far. This minus 1/3 cancels with this plus 1/3. This minus 1/4 cancels with this plus 1/4. Will the 1 ever cancel with anything? No, there's never going to be another 1. Will I ever get 1/2 again in these terms? No. So I kind of go until I see that the first, like, whatever this term is going to cancel out with something. And so I'm looking to see, like, where will it cancel? The 1/5 will cancel. If you're not sure of that, then write some more terms. The next term is going to be 1/5 minus 1/7. So yeah, so all of these are going to cancel. And then when we stop, we're coming up with an nth partial sum here. When we stop, we're going to get 1 over n minus 1 over n plus 2. And I messed up my notation a little bit on this, sorry. What we should be doing is a limit as well. So, well, no, never mind. We can do this for a partial sum. So this is, let me just get rid of my equal sign here. So this is the nth partial sum is what I'm coming up with here. 2 times all of these, and it's because I'm stopping at the nth term. All right, so then what are we supposed to do? To find the sum, the true sum of this infinite series, we're supposed to take the limit as n approaches infinity of whatever the surviving terms are in this partial sum. So we definitely have a 2 on the outside. This 1 is here, plus 1/2 is there, and then everything else is going to be canceling out. This 1 over n would have canceled with the previous term, which would have had a 1 over n in it, or somewhere there would have been a 1 over n to cancel. This will survive because there are no terms coming after it to cancel out the minus 1 over n plus 2. So as I'm going through and taking this limit, I'm getting 2 times, this adds up to 3 over 2, minus 1 over infinity. So I'm getting 3. And instead of capital S, you could keep it as capital S, but what does capital S represent? It represents the infinite sum, or the actual sum of adding infinitely many terms, I should say, of this series. It's the sum of the series. So this is one of those telescoping, sort of. We call it telescoping because if you expand it out, a bunch of the terms cancel out and this thing collapses back in on itself, but you are just looking to see what survives. Now, number 49 is not telescoping, even though we're subtracting 2 terms, because both of these have a power to the n. So this is really just 2 geometric series. So let's separate it out, first of all. I don't like to keep them together like that. And I'm going to rewrite 1 over 2 to the n as 1/2 to the n. And then we're subtracting the sum from 0 to infinity of 1/3 to the n. And we know that both of these have finite sums, so we can go ahead and find their sums separately and then add them together. So for this one, r is 1/2, a sub 0, because it starts at 0, is 1. So this one is going to be 1 over 1 minus 1/2 minus, over here we're going to get 1 over 1 minus 1/3, because r is 1/3 and a 0 is 1. Okay, and then what do these two things add up to? So this is 1 over 1/2, 1 over 2/3. So that's 2 minus 3 over 2. 2 minus 1/2 is 1/2. All right, the repeating decimal problems. So we had something like this in our notes. So the first thing to do is kind of expand it out. 0.818181 ... And you're looking at where the pattern is. So there's an 81 that's repeating. That's how you want to think of it. The first 81, this 1 is in the hundredths place. So this would be equal to 81 over 100 plus, now this is 81. So this is the hundredths, thousandths, 10,000ths. So this is 81 over 10,000. Another way to look at this is like, see how I had 2 zeros here? Now I've got 4 zeros. The next one, if I want to write it out, I'm going to put 2 more zeros on there. So now I have 6 zeros. So this is the millionths place. Okay, so, and then it would keep going. And remember, you do not have to overthink this. You can just say, here's my first term. A is 81 over 1, A sub 0, excuse me, is 81 over 100. And what is R? R is what I get when I divide any consecutive terms. And we know that this is geometric. Any repeating decimal is geometric. So I can just divide the first two terms. I'm going to do this will be easier in exponent form. 10,000 is 10 to the fourth. 100 is 10 squared over 81. So the 81s cancel. 10 squared over 10 to the fourth is 1 over 10 squared. So that's R. R is 1 over 100. And then what we're saying is 0.81 repeating can be set up as a geometric series. Starting at 0, it would be A sub 0 times R to the n. And you can double check. Do I get the fractions I'm supposed to get? When I plug in 0, I get 81 over 100. Yes. When I plug in 1, I get 81 over 10 to the fourth, right? Which is this. Yes. So it is going to keep working. And then my goal is to, so write the repeating decimal as a geometric series. Done. That's done. That was part A. And then part B is like, go ahead and find the sum of that geometric series. So that series equals A sub 0 over 1 minus R. And that's 81 over 100. So this is 100 over 100 minus 1 over 100. So 99 over 100. Multiply by the reciprocal. 81 over 99 reduces. If I divide by 9, I get 9 over 11. And you can check this. 9 over 11 does give me 0.81 repeating. All right, for this one, explain any differences among the following series. So we've got the series from n equals 1 to infinity of a sub n versus the series from k equals 1 to infinity of a sub k versus the series from 1 to n equals 1 to infinity of a sub k. So let's expand out some terms because we're supposed to compare them or look at differences. So this first one would be a1, sorry, my colors to coordinate, would be a1 plus a2 plus a3, dot, 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 an, and it would just keep going. The next one would be the same thing, k equals 1, and now it's a sub k. So nothing really changed between the first two. They are the same. Notation, the input is different, I guess. But otherwise, you're going to get the same terms if a sub n equals a sub k. So these are essentially the same thing. C is different because if this says you're plugging in when n equals 1, but a sub k means you'll have some expression in terms of k, there will be no n's to plug in for. So this one I can't plug in terms. I can't remember how I'm sure I worded this more articulately on the PDF of this key, but you can't plug in terms if the input is different than the summation bounds. I'm going to say summation input. If this says n and this says k, there's not going to be anything for me to plug into. Just like if I had f of x equals 2w plus 3, I wouldn't, there is no x to plug into if I were trying to evaluate that. And then 82, I just crossed it out. We did that on homework 11. I didn't mean to include it here. All right. We have problems like this that we'll look at throughout the chapter. We definitely have something like this on our quiz too. Find all values x for which the series converges. For these values of x, write the sum of the series as a function of x. So what does this mean? So first of all, these are set up to be in geometric form, right? It's a constant times something to the n. So what we're saying is this is a geometric series, and it will converge as long as the absolute value of r is less than 1, right? and, well, between 0 and 1. But that means that r itself can be anything between 1 and negative 1. And then what is r in this case? R is the expression in the parentheses. So we need x minus 3 over 4 to remain a fraction that will sit between negative 1 and 1. So solve for this. So multiply both sides by 4. And then, oops, that's still x minus 3. And then add 3 to both sides. So any x value between but not including negative 1 and 7 will cause this to be a fraction that's between 0 and 1 in absolute value. So these are the x values that would make this series converge. And then what would it converge to? So to find the sum, you're saying, well, a sub 0 would be, if I plug in 0 for this, it would just be 4. And r is the expression x minus 3 over 4. So we're not doing anything with these numbers, really. So what would this series add up to? The series from 0 to infinity of 4 times x minus 3 over 4 to the n, it would add up to 4 over 1 minus x minus 3 over 4. Now we need to clean that up. This could be a multiple choice, or would almost definitely be a multiple choice answer. So I would be looking at like which one is equivalent to this. Now, if you multiply, you could do common denominator, or if you multiply by 4 over 4, you get 16 over 4 minus parentheses x minus 3. That's important. So that's 16 over 7 minus x. So this is the sum. And again, this is only the sum for x values between 1 and 7. So if you have an x value that's outside of that little domain set, then this series would diverge. All right, for number 87, same idea, just less math. Now it's only an x to the n. I guess you could make this, you don't have to do this, but you could make this, I guess I will, negative x to the n. So this again would be a geometric series. I'm only doing that for like when I do the sum of the thing. That's the only time that matters. This is a geometric series that converges if the absolute value of r is less than 1 or between 0 and 1. I always am going to expand this out to just saying r needs to be between negative 1 and 1. You could start right there if you wanted. And then what is r? R is negative x. Okay, and then if I divide by negative 1, remember that flips everything. So that would be like this. So don't overthink this. This is just, if you just have an x or a negative x, x needs to be between negative 1 and 1, right? Bigger than negative 1, smaller than 1. Okay, so then what would a sub 0 be? If I plug in 0, either in here or in here, I would get positive 1. Negative 1 to the 0 is positive 1. And then r is negative x. So you do need to get the sum of the series, you do need to simplify that. So what would this series add up to? This would be 1 over 1 minus negative x, which is just 1 over 1 plus x. And again, that's only true for x between negative 1 and positive 1. And I'm just going to talk through the true or false section here. So 123, if the limit as n approaches infinity of a sub n equals 0, then the sum from 1 to infinity of a sub n converges. So remember, this is just saying if the terms approach 0, is it guaranteed that you have a sum that converges? We will get more into this as we learn more tests. This is false because even though so far that has been true, like when our geometric series is approaching 0, we get something that converges. It's just like in chapter 8 with integrals. If the terms are not approaching 0 fast enough, which we will learn what's fast enough and what's not, then that sum will not be finite. So if you're not adding 0 quickly enough to the sum, you are adding enough to let it keep growing. We will talk about the harmonic series shortly, and that is something that fits the bill. Its terms approach 0, but it diverges. Okay, so more on 123 later. 124. If this series has a sum of L, and we start at 1 to infinity, then the series that starts at 0 to infinity would be L plus A sub 0. So that's true because remember, this first series is A1 plus A2, etc., and that adds up to L. This series would be A0 plus A1 plus A2. So yeah, it's going to be L plus that first A0 term. If the absolute value of R is less than 1, then the sum from 1 to infinity of A times R to the n would be A over 1 minus R. So this is false. This is a common mistake. Remember, it matters what you write here. If they would have written A1, like the first term when you plug in 1, then that would be correct. But in general, they're just saying A, just this number, and that's not right. It will be, if you plug in 1, you'll get A times R. It would be whatever A times R is over R minus 1. Or if this said n equals 2, it would be, the first thing I plug in would be AR squared over 1 minus R. All right, for this one, this series diverges. So this is true because if you take the limit as n approaches infinity of just the terms are approaching 1 over 1,000 because you have n over 1,000, n plus 1. So this equals 1 over 1,000. So even though the terms are approaching a number that's very small, that's not 0. So the terms do have to be approaching 0. We'll talk about this again, I think, tomorrow. The terms do have to be approaching 0 to even have the possibility of convergence. For 127, is 0.75 equal to 0.4749 repeating? I did the math on that. So again, I'm almost out of time here before office hours, but you can check my math on this. I set it up to be 74 out of 100, and then the repeating part is really right here. So this is just hanging out to be added until the end. This is what you're trying to create the series for. So A sub 0 is the first term. I divided to get R. I came up with what that sum would be, and I did some math. So it turns out it's true. And then 128, every decimal with a repeating pattern of digits is a rational number. So yeah, we should be able to, as long as we have a repeating pattern of digits, we should be able to use the same process to come up with a geometric series. And every geometric series that converges has a sum. All right, that finishes this homework assignment, and we've got more tests to learn. So if you're having trouble with any of these, please make sure you ask about them.